So good news, this is looking dope right now. Look at that. After a few adjustments, this is the same setup for the most part, we end up with this. And this is about 100,000 pieces, and this really didn't take that long to sim either. That's the beauty of packed geometry. We get a whole lot of bang for our buck in terms of detail and the amount of stuff in there without totally destroying our sim times or our render times. So great. Let me give you a quick tour of what I just did so that we know what happened. It's basically the same setup. If I didn't mention this before, if we go to our RBD configure, we're talking about the small pieces, right? Before, we mentioned that the small pieces are going to be boxed like that for the collision hole, but also I said to ignore other packed pieces. So all the tiny little pieces are ignoring all the other tiny little pieces. That'll really speed things up quite considerably, so it's worth doing that collision ignore attribute for the tiny pieces. In addition to that, we also have some adjustments made on this velocity noise right here after the wrangle. So I didn't do anything different with the wrangle, but if we go here and we take a look at these velocity trails, I did go ahead and change these. What I did for this is I set it to multiply, minimum value of 0, maximum value of 1, and the key here is to uncheck this output raw value. And what that means is that if this is checked on, most of the values are going to be around 0.5. If you turn that off though, then the values start reaching closer to 0 and closer to 1 more often. So in other words, it adds a bit more contrast to the noise that we're trying to multiply against our velocity. And that's good because it allows us to have these more defined shapes. So we can kind of see this visually along here, how we have these guys more defined. And that's because I unchecked this output raw value. Besides that, this is all kind of, the same sort of stuff. I just played with it a tad bit. We also have something different here in the DOPNet, where I brought in this SOP solver where we deactivate things if the pieces go far enough down. So we already talked about that, but there's another optimization that you can do, and that is if we go to this bullet tab and we turn down the number of constraint iterations. Because the thing is, we don't really have any constraints going on. And because of that, it doesn't make sense to spend a lot of time thinking about that. So if you turn the iterations down to 1, that'll also speed up your simulation quite a bit. We also have drag spin, and that's about it. I also cached it out right here. So these are all things that I've talked about before. Hopefully that's not too challenging for you at this point. But after doing all that, we end up with this. Oh, and I also want to mention that I changed the size distribution. So if we go up here to our P-scale, which is this guy, most of the pieces are really, really small, and only a very select few of them end up getting larger right here. Okay, so at this point, what can we do to improve this? Well, we don't have any angular velocity. And so if you look at these pieces, none of them are spinning around. And that's going to add a lot of interesting motion to this whole thing as well. There's multiple ways of going about this spin, but probably the most straightforward way is to create a pop spin right there, plug it into the post solve. We can go right here with that. And all we need to do is specify a spin speed as well as a axis for this to spin around. So just to visualize what the axis is doing, let's say that we have a particle and we want to spin it. Well, if we imagine, let's say, twirling a toothpick, if you've watched my quaternion stuff, you kind of know what I'm talking about. We have, let's say, an axis right here that's defined. It's a vector relative to a piece's position. And whenever we do the spin, we're saying, hey, go ahead and spin around this particular axis. It's kind of like twirling the toothpick, right? That's what we're specifying here with the axes and the spin speed. Now, if we go into this pop spin node, we can see how this is built. And all this is really doing is using a pop VOP and it's adding some things right here to create the spin. So if I take a look at what's in here, I can get an idea of what sort of local variables are being used. And based on what I find, I can then use the vex snippets to call on those variables and set them myself. So here I have the parm2. I can see that this is using spin speed. And we also have axes right there. So I know that if I go to this vex expression right now, and I say spin speed, it already knows what I'm talking about. I don't need to define what spin speed is because it's already being used in that VOP. Likewise with the axes. So if I say that, I don't really need to say anything else because it knows what I'm talking about. So let's say that our axis is a random value based on the ID of the particle. And let's also subtract a vector that's something like this. And the reason why I'm subtracting a vector like that is so that we can have a random axis in all directions. So if we think random ID, that's a random value between 0 and 1. And when we take away 0.5, that means that the maximum value is now 0.5 and the minimum value is negative 0.5. That means for x, y, z, we can have positive or negative values going in either direction. So that basically gives us the random orientation of the toothpick. Now for the spin speed right here, we can specify a random value as well based on the ID. And we can just multiply this times something really high. So let's take our spin speed to 1 as an example for now. And also we need to say at ID when we do that. And now let's say that I go forward a few frames and we check this out. We should see the rock spinning in random directions now. So now we have something like this, which it's a little bit hard to tell, but we are now rotating like so. It's also going to be important to only activate this during the creation frame. So we can keyframe this activation so that it correlates with our creation frame of the pieces. So that's going to be frame 25. Set this to manual. And if we say 25, activation of 0, well, actually, that's going to be frame 24. And then on frame 25, activation of 1, 26, 0. Okay, so now, as we go forward and simulate this, we ought to see some spinning. And sure enough, we do. It adds a nice bit of motion to it. I think, especially as the pieces settle down, it's nice to see them roll around a little bit. And I think that this is a pretty solid place to be for right now. In the next video, let's move on to something else.